Today we are going to do the fifth video in our three-part series on building a laser communicator. I originally said this would be a three-part series, and in a way it is. We had our first part, which was the concept. This will be the second part, which is the design. And our third part will be the actual build. But I made 3 supplementary videos as I tested the laser to see what parameters we needed to work with there, tested the microphone to see what parameters we needed there, then I tested the laser and the photodiode together to see what we needed to work with. So now we have enough information to actually start the design. So let's take a quick look at the concept again. We start out with a microphone that is putting out a signal that is centered on 0 volts, and the microphone we tested, we found out, put out a signal of 20 millivolts peak to peak. So coming off the microphone, centered on 0 volts, a 20 volt, 20 millivolt peak to peak signal. So that's what's coming off of there. The first thing we need to do is offset that to the voltage we need to work with at the other end. Let's look at what that is. We have the laser diode. There's no standard symbol for a laser diode, so I'll make it a diode with a little star on it. That's going to go to ground. And we determined that we needed 3.5 to 5 volts to make this operate in a linear region where it's reasonable to expect some signal with no distortion. So this is 3.5 volts to 5 volts. That's 1.5 volts peak to peak. And we want that centered on the middle of that, so that's going to be centered on about 4.25 volts. So we have to get the signal from the microphone to the diode from centered on 0 volts, 20 millivolts peak to peak, to centered on 4.25 volts, 1.5 volts peak to peak. And so we need the circuitry to take care of that. First we need to have some kind of a voltage shift or offset. We'll call that our VS, some circuit that does that. Then we need to go through an amplifier, which will amplify our signal. Finally take that to the diode, and that's the diode end. On the receiving end, we're going to use a photodiode. So a similar arrangement, except the photodiode will be, of course, reverse biased. And there is a standard symbol for a photodiode. We have a little arrow, a little zigzaggy arrow pointing to the diode, showing that that is a photodiode. We'll need a little bias on there, so some bias resistor. And off of this will come a signal. We had a range of 0.04 volts to 0.14 volts. So that was our range when we had the laser diode going from when the laser diode went from 3.5 volts to 5 volts. The output of the circuit here went from 0.04 volts to 0.14 volts. And so we have to amplify that to something reasonable to drive a speaker. Plus we have to have a voltage offset circuit, another voltage shifter, to take that down to be centered on 0 volts and go to a speaker. We don't know exactly what the speaker is going to need, and we probably won't until we actually start the build-up. And so our design of how much amplification we need is probably going to happen as we do the build, somewhat experimentally by trial and error. So that's the basic design. Once again, coming off the microphone, centered on 0 volts, 20 millivolts peak to peak. Shift that voltage up to 4.5 volts centered, to where we have it going from 3.5 volts to 5 volts, making that 1.5 volts peak to peak. That laser is going to shine over at our photodiode. Coming off the photodiode is going to be 0.04 volts to 0.14 volts. Amplify that, shift it back down to 0 and out of the speaker. Before we start looking at how I'm going to design our circuit, let's look at how Kip K solved these problems. Once again, microphone, voltage shifter, amplifier, laser. Kip K's video, he solves the amplifier and the microphone by simply using a radio. So basically the microphone is in the radio studio and the amplifier is in the radio itself. So we end up with a signal that is coming from the weak microphone, a stronger signal that has been amplified, ready to go to the laser diode. So how did he solve the voltage shift? Well, let's erase this and just draw his basic idea for his circuit. He started out with the radio. Output of the radio is already amplified, ready to go. We needed the laser diode. So he had a circuit here. Let me draw this a little differently. You'll see why in a second. Had a battery to run the laser diode. And the way he did his voltage offset is certainly worth mentioning because it's a common way to do this. He put a transformer in here. And so what happens, we have the DC voltage running through this circuit, running the laser diode. And when the alternating current comes in, well, when that voltage is going up, the magnetic field around this coil is going to be building, and then when that voltage goes back down, that magnetic field will collapse. And depending on the orientation of the actual connection, let's just assume it's connected such that when this voltage is going positive, the magnetic field builds and collapses in such a way that it pushes back on the current. So it pushes back more and more, pushes back less and less. Then when the polarities flips, it does the opposite. As the opposite polarity of magnetic field comes across, it pushes, and so it aids the flow of current in here. So during half the cycle it pushes back, during the other half of the cycle it pushes the other way, and so that basically acts like a variable resistor in one way. As it's aiding the current flow, it's acting like a small resistor, and as it's pushing back, it's acting like a big resistor. That's one way to look at it. It also does add energy to the circuit, so when the orientation is such that it's aiding the flow, it actually increases the voltage across the diode more than the battery has. And when it's pushing the opposite way, it decreases the voltage across the laser diode. So we end up taking the DC voltage and simply adding the AC to it by coupling with a transformer. Very simple, easy way to do. And so Kip K's transmitter was just a radio, a transformer, battery, and laser. Very easy way to build it. We're just going to be doing it a slightly different way. So let's look at how we're going to build the transmitter. We start out with a microphone. Once again, coming off the microphone is centered on 0 volts, and it's 20 millivolts peak to peak. The first thing we're going to do is give our offset. So what we're going to do is put a voltage divider here. And we want to choose these resistors such that it puts the nominal voltage here at 4.25 volts. We're going to start out with 9 volts because we want to power this with a 9-volt battery. So that's how we'll choose those resistors. We'll look at how we'll do that in just a moment. But one important thing is we don't want this DC voltage going through the microphone, so we have to block that with a capacitor. So there's our voltage shift circuit. Oh, and by the way, since this is going to be a condenser microphone, it also has to have its own bias. We'll just draw that right in there. That will also go to the 9 volts. Let's get this out of the way here. Draw that a little nicer. So plus 9 volts and a resistor. So there's the bias resistor for this microphone. And we discovered that the value of this resistor is not really critical, roughly 1 to 2K, maybe 1 to 5K. Let's just say it's 2K just for a good average resistance for that point. So that biases the microphone. We have a capacitor to isolate the microphone from the other part of the circuit. And then we have this voltage divider to bring that up to 4.25 volts. Now ideally, we would want this voltage at 4.25 volts, but that's pretty close to the halfway point between 9 and 0. So if we make these two resistors equal, that'll give us a nice 4.5 volts. The compromise is that we're raising our center point a little bit, so if we use our full 1.5 volts peak to peak, when we're speaking at the highest level, it's going to drive that above 5 volts, and we don't want to do that. So we'll want to reduce our gain just a little bit. We could be more precise and choose some resistors, but they're going to be hard to find in the standard resistor values. So either we've got to fudge a little bit or use a potentiometer here. So for perfection, we could use a potentiometer. I think we'll just center that on 4.5 volts and reduce our gain just a little bit. So let's simply make these equal resistors. To reduce the amount of current we use, let's make them 10K each. So there is our voltage that's going to be centered on 4.5 volts now. And now we need to send that into an amplifier. And what's the easiest way to do this? Simply a operational amplifier. So we'll make this a non-inverting amplifier. So here's our op amp output. And that's going to go into our positive input, or our non-inverting input. That will go into our inverting input. All we need to do is decide what these resistors need to be to get the gain we need. So we want to go from 20 millivolts peak to peak. Let's write that as 0.02 volts peak to peak. We want to bring that up to a little less than 1.5. Let's just make that 1 volt peak to peak. So 20 millivolts up to 1 volt. Pull out my trusty calculator here. I can't do any math in my head. So that's going to be 1 divided by 0.02 equals, gives us a gain of 50. That's not too bad. Might be able to get away with that in one stage. To get the gain we want without losing bandwidth, we might have to use 2 stages. But let's see if we can do this in one stage. So we need a gain of 50. This is a non-inverting amplifier, so our gain is going to be 1 plus R2, R1, R2 divided by R1. So we want to have a 49-to-1 ratio there. Yeah, okay, let's compromise there and just make it a 50-to-1 ratio. So how about simply 500K and 10K? Plenty of resistance, so we don't have too much current flowing through the feedback loop, and that will give us approximately what we need out here. So we're doing a little bit of fudging, but we're probably well within the ballpark that we need. And so now we have our approximately 1 volt peak to peak centered on 4.5 volts, and we simply have to run that to the laser diode. And the problem is, we determined we needed about 50 milliamps. I'm going to use a 358 here. Why? Because I have some 358s. Only 49 of them. Paid $6 for them on Amazon. You know, why not? So I'll use the 358 there. I think I have to look it up. I think we can expect maybe 30 to 40 milliamps out of it. That's not going to be enough to drive this, but that's so easy to fix. All we need to do is put a simple NPN transistor here. Let's get this out of the way. And drive our diode with that. And the only change we might want to make is simply take the feedback from here instead of at the base of that transistor, just to make sure we understand what's going on here. Let's put a little loop there. So there is our transmitter circuit. Pretty much ready to go. So we have about a 2K resistor to our condenser microphone, capacitor to separate the DC from the AC, 2 10K resistors to put this at 4.5 volts, going through a LM358 with a gain of 50. To bring this up to about a 1 volt peak to peak, and through the transistor to give us enough current. And there is our transmitter circuit ready to go. So the next thing we need to design is the receiver. And so that starts off with a photodiode. Oops, that needs to be reverse biased. So let's draw it upside down. If I remember right, I think we used a 10K. Was that a 10K or a 2K? I think it was a 10K resistor. It's not going to be incredibly sensitive to what that resistance is. That's going to come off of here, and we got a range of voltage of 0.04 to 0.14, so that's going to be 0.1 volts peak to peak. Now, once again, I'm not sure about what we're going to need to drive our speaker. We might have to tinker around with our gain. But right here, we want to do about the same thing we did with the other circuit. We want to raise this to about 4.5 volts because that's halfway between the 9 volts and 0 volts. We have plenty of room for the alternating current, which is going to be centered on 4.5 volts again to begin with. So we will put a bias circuit here. Same thing again. Two 10K resistors. And this will go to our amplifier. Once again, a non-inverting amplifier. Sloppy resistor there. Let's make that look a little cleaner. A little too close to my resistor there. It was making me nervous. Okay, and back to here. Non-inverting input, non-inverting input. And there's the basic amplifier. We don't know what this gain is going to need to be, so we'll leave that open. Maybe we'll put a potentiometer there and experiment with it, and when we get the right gain, we can replace that with discrete resistors. And so then that has to somehow go to a speaker. And now comes a bit of a problem because we want alternating current going to here with no DC offset. And there's two ways I can approach that. I could use a transformer coupled push-pull amplifier, but that's kind of expensive. I need two transformers and it gets kind of big. So I want to do a transformerless push-pull amplifier. So that's going to be something to the effect of this. I'm going to need two complementary transistors, a PNP going to our plus 9 volts, and that's going to go to an NPN down to ground. Now normally for a transformerless push-pull amplifier I need to put some bias, something like this here. A couple of diodes. And we'll couple it. And of course this would be a minus voltage. But since we're using an op-amp, we can take our feedback from the output and the op-amp will compensate for our offset here so we don't get crossover distortion. The problem is that as this goes positive, this transistor will not turn on until this gets up around half a volt, 0.7 volts. And then when it goes negative, this one won't turn on until it goes to about minus 0.7 volts. So there's a no man's land in here of about 1.5 volts where these transistors are not conducting, and so we end up with an output that looks sort of like that with severe crossover distortion. But we can take the feedback that goes into the op-amp from the output and that will compensate for the crossover distortion. So we don't need that. So we can feed that directly into these. This will go to the speaker. Speaker goes back to ground. And we just need a fairly heavy capacitor right here to take out the DC voltage. So our got that plus 9, we got the voltages right. And so this is going to sneak over to here and watch this voltage here. So it'll give us the right gain at this point to swing this up as high as 9 volts, down as low as 0 volts. And then this capacitor will filter out the DC and only AC will go to the speaker. And I'm kind of designing this off the top of my head. We might have to do a couple of little tweaks as we build it. But there's the basic circuit. We don't know what our gain is going to be, so we'll put a potentiometer there to begin with. And so, other than grounding our diode here, there is our receiver circuit. Oh, I forgot to mention how Kip K solved the problem. We'll just draw that down here real quick. He used a photocell, and ran that to a little amplifier module he bought at Radio Shack. So he had a pre-built amplifier. We're building our own amplifier. And so that was a photocell. Ground that. Well, I'm not going to, we'll just draw it this way because he did not use an op-amp, so I don't want to draw an op-amp circuit. He just had an amplifier that he bought, and that went to a speaker. So real simple circuit. What he did is just bought an amplifier and had the speaker built into it. So photocell, amplifier, boom. As a matter of fact, when we're testing the transmitter, we'll probably use the same kind of idea. My thought is I'll use a photocell and run that into a computer speaker. When we test the amplifier, then we'll build the receiver. Okay, so there's the receiver circuit, photodiode, bias that I think we did with 10K. We can play with that to get the best bias for that. A capacitor to separate the DC from the AC. Well, at least keep this DC from that. This is going to be DC also, with DC with AC on top of it. So over here we'll have about 1 volt peak to peak centered on about 0.09 volts. Then we'll have 1 volt peak to peak centered on 4.5 volts over here. Amplify that. Looks pretty simple here, 2 transistors. My only thing I need is a complementary pair. So off the top of my head, I don't know exactly what those will be. We'll look them up when we build the circuit. But a little transformerless push-pull amplifier. I don't need the bias here because of the way the op-amp goes into it. Cross fingers, I'm pretty sure that'll work. If it doesn't, we'll fix it when we build the circuit. Capacitor to separate the DC from the speaker, so only the amplified AC gets to the speaker. So there's the design. That's what we're going to build, and our next video will be the actual build of the circuit. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.